to the Elite Weather Forecasting channel. My name is Dooley the Doe, and I've been excited to do this video here, and I've been kind of preparing it for a while here, but we're halfway through spring now, and we're going to be coming into a summer in just a couple months. And one thing that we're all aware of is how bad severe weather can be out there. And right now we're going through quite a spell of severe weather, as our severe weather season appears to be quite active, despite there being a La Nina season. I think it's actually enhanced by La Nina, but we are seeing extended cold spells across the northern half of the nation, as that cold air continues to spill in from the northern Rockies and out of Canada over to the upper Midwest. The northern plains and the Great Lakes have been cooler than average this spring, and it has struggled to warm up consistently. But we have been seeing those warmer conditions across the deep south, the southern plains, the state of Texas, and also as well as into Florida. And that heat across the south is interacting with that cold across the northern plains and the Great Lakes. And there's a very sharp cutoff between where temperatures go to the 70s, 80s, and even the 90s in some cases. But we'll have those 30s and 40s here across the northern plains and the Great Lakes. And it's that battle zone that's been setting the stage for multiple instances of severe weather across the central and southern half of the nation on over into the East Coast. We've had a few instances where that severe weather has spilled into the northern plains and the Great Lakes, and we're probably going to see our most significant instance of that this coming weekend, as we're going to see that severe weather come to the northern plains and the Great Lakes. But let's jump into this video as we examine some of the aspects of severe weather and what you can do to prepare and protect your family and your property from damage during this severe weather season. So as we, hang on a second, let me click on something here so that my clicker works. All right, let's go. All right, so here we are. We are looking at what is a pulse thunderstorm. This is called a pulse thunderstorm. This is a generic garden variety thunderstorms. And what creates these is you get that heat in the afternoon. You don't necessarily need an area of low pressure, but they do need a trigger typically, and usually that trigger is a cool pocket of cold air aloft in the upper levels of the atmosphere. We often call those troughs of low pressure, or a short wave of low pressure. It's not really a rotating, spinning column of low pressure like you typically see with an extratropical storm, but it's usually just like a cool pocket in the upper levels of the atmosphere where the temperature might be cooler than the air parcels around it. So it creates that cold bubble, and that cold bubble kind of sags down and compresses onto the atmosphere. And what it does, it causes the air that's warmer around it to rise, because you have a situation going like this, that compression, and then it causes the air around it to rise. So that rises and it gives birth to these types of thunderstorms. These are the thunderstorms you see on a summer afternoon in July, when it's a beautiful hot day, and then you get that a sudden brief shower or thunderstorm. This is usually the case. These storms build up the convection, the cumulus clouds rise, and you see those big billowy cumulus clouds, and eventually you start to see an amble. You'll see it at the top where it kind of spreads out like feathers at the top of the thunderstorm. But what these storms tend to do is they rain themselves out. They build up, the rainfall starts, and when it falls, it shuts off that updraft. That cold air coming down with that rainfall suppresses the updraft, and which usually causes these storms to dissipate. They lose their energy once that warm updraft is shut off, because of that cold, cooler air coming from the top of the storm with that rainfall. So here's a look at what a supercell would look like. Now, supercells are quite complex thunderstorms here. And these storms usually need a trigger, a cold front, an area of low pressure, maybe a mid-latitude low pressure center, a trough, or some kind of significant trigger that may be in the area that can create a focus for these storms to kind of congregate around. And with these storms, you usually have that, like when you have a cold front or a warm front, you have that air that travels a great distance until it meets up with that cold front, and this is what's called forcing. So then that warm air, that updraft, is forced upward, and as it rises upwards and it begins to precipitate, then it creates the downdraft. This is the air that comes down in the rainfall. When you see a thunderstorm and you're coming up to it and you feel that wind out ahead of the thunderstorm, that's that downdraft coming out, and it creates what's called an outflow boundary. So it's kind of like a mini cold front associated with the thunderstorm, and usually that air that flows inwards gets caught by the updraft, and there's usually, you have wind shear. When you have that wind shear, that's air blowing in at two different directions. You have a southerly or southeasterly wind flow at the surface. Maybe at the mid-latitude, you may have a southwesterly or westerly wind flow. And when that meets, it creates a spinning column like this. It's a horizontal column. And once that updraft hits that column, then that column is lifted and turned upright. So now that spinning column is turned upright because it met up with that updraft coming in, and you have that cold draft, that downdraft on the backside. So that now that it's spinning like this, you get the formation of your wall cloud. That is what creates your meso. That's what creates those wall clouds that you see in those big supercell thunderstorms that usually leads to the development of your tornado, because now you have that spinning column of air through your clouds, and when it reaches the top of the cloud at your cap, and then you see it outflow, that goes off into your anvil. So it's kind of like an exhaust for the storm. You see it also with hurricanes have an outflow at the top of the cloud. So that's what makes thunderstorms look bigger than they actually are. When you look at it on the radar, you may see a big, huge cloud, but that only a small section of that cloud is actually experiencing the thunderstorm or the precipitation from that thunderstorm. And then you have your rear down, your flanking line here, which is another area of inflow that outflow into the thunderstorm, because when that air comes in to your tornado and it begins to rotate through the wall cloud, through the cloud structure itself, into the upper layers of the troposphere. It goes to the troposphere, meets the tropopause, and sometimes your overshooting cap can enter into the stratosphere on the most severe of those thunderstorms. So now you have your rear flank downdraft, and you see your gustnados here, and this is what you would call the bear's cage. If you're between, say here where the rain shaft is, maybe your tornado there, and here you'll kind of see like dust in the air in this whole region, maybe some debris or things in the air. That's called the bear's cage. That's probably the core of your storm, and it's the most dangerous part of the storm that you won't want to be in. Another type of storm we have is a multi-cell thunderstorm, and these are thunderstorms that they kind of like pulse thunderstorms, but they're regenerative. They're kind of like the Borg of thunderstorms. They kind of adjust to the area, and you'll see a thunderstorm develop. Maybe you'll start to rain off, but it's when you see those thunderstorms where it just doesn't seem to stop. What you're really experiencing, it's not really one thunderstorm that you're experiencing. Thunderstorms aren't very big as far as size is concerned and how much land they cover. But what you're seeing is new storms constantly replacing dissipating storms. So you'll get older storms out in the front that dissipate, but new storms kind of come in. Well, actually, they're moving. This storm is moving this way. So you'll get the storm build up, rain itself out, but you have other updrafts out here that's going to build in new cells. So you're going to continue. Often we call this training as well. It's when you have thunderstorms that constantly move over the same area, and you're getting hit repeatedly with thunderstorms. Here in the northern plains, we tend to see this in late July and August. We'll see situations here in Minnesota where thunderstorms kind of build in, especially overnight, because you have a nice low-level jet that kicks in and causes those storms to develop, and you just have a repeating cycle of thunderstorms as long as the conditions exist and you have your support system in place to support those updrafts and cause that forcing to get those storms to develop. And you may see storms rain themselves out, and you might think, oh, maybe the storms will be over, and they just keep coming. So that's when you get those multi-cell thunderstorm complexes. Now this here is your MCS, this is your convective, your MCS thunderstorm, multi-cell convective system. So these are one of my favorite thunderstorms and very interesting thunderstorms. And I posted another video. I got another video of MCS actually taking place across Missouri this evening. I have a live video of that cell on the radar and what it would look like on the radar. It's really fascinating. You guys should check out that video as well. But you're going to see this here. Now, this is also another form of a multi-cell thunderstorm where they're kind of regenerative. As your storm moves this way, usually how you experience these guys is that you'll see the thunderstorm. This is when you see that shelf cloud. You may see that long gray cloud, or maybe it might look white depending on the time of the day and the angle that it's coming from, that's stretched across the front of the sky. And when that thing passes over, then you feel that gust of wind, because what you're feeling is right here. You have the inflow, you got the updraft right there, but you're feeling the downdraft. This is the air coming downward out of the storm, spreading out on the land out ahead of the storm, and this helps to create an outflow boundary, which will help generate new storms out ahead. Now that can actually contribute to the death of these guys, because the storms that these generate as they move along, they actually help this to stabilize the atmosphere, because they create new storms out ahead of them, because they cause air that hasn't been disturbed by a storm yet, that's still juicy and ripe for thunderstorms to develop, because they create a cold front out ahead of them. They usually protrude out maybe several miles out ahead of these big mesoscale convective systems. And I'll show you what one of these look like on the radar, but you'll get this guy going, and these actually feel like they can last for quite a while because they're very huge. These are some of the larger thunderstorms, and what you're seeing is that you'll experience a brief period of very heavy rainfall, gusty winds. You'll see all the lightning. You might see some hail with some of these guys. They can produce torrential rainfall. These are your real rainmakers of the thunderstorm family, and you'll see these guys, and they have several updrafts going in there. They're regenerative. They kind of re-go because they have kind of a central low pressure center that kind of helps to create that live for them and gives them that support they need to live. And then once you pass the initial burst of the really gusty winds, it kind of settles down a little bit. You'll see just general rain. It might rain a little bit hard, but you'll see a lot of lightning. You'll see, now here, usually with these guys, it's hard to see the lightning because of the heavy rain. So oftentimes you don't really hear the thunder because the rain kind of disrupts the wave pattern of the sound, so it deflects it a lot away. So a lot of times you'll see all this lightning but not really hear much thunder because of the heavy rainfall and the interacting of the sound. Here's your physics in play for you, and the sound cannot penetrate those heavy sheets of rain, so the thunder is often mumbled or sounds like it's coming from a distance. But usually these are kind of interesting storms because as they move along, once you get past that initial shock of the main gust front and the main initial band of heavy rain, then you'll see just maybe moderate to slightly heavy rain. It's more steady rain. You'll still see lightning dancing around in the clouds, but you really won't see that cloud to ground lightning. You typically see the cloud to ground lightning on this side of the storm. As the storm approaches, it's where you'll typically see the cloud to ground lightning. You may see some lightning in the anvil here. You'll see lightning as well in the rear part of the anvil. This is what you get those spider lightning and anvil crawlers. So this is where you see the lightning dancing around in the upper levels of the clouds there. It's really pretty. These are really spectacular thunderstorms. Now we're dealing with another angle of these mesoscale convective systems. So another MCS here, and you'll get an issue where you have a lot of divergence taking place. A lot of winds is going in different directions here. You have this steady updraft. You usually see this kind of storm associated with warm fronts. Now, warm fronts don't always produce thunderstorms, but sometimes they can, especially in the spring and summer months in the United States. They can often produce severe thunderstorms as well. But you see this inflow. This is more of it's not really a hard convective storm, but what it is, it has those aspects of convective storms, but you see that cumulus congestus here out ahead of the storm. This is one of those storms where you see just a variety of clouds. You're like, man, what's really going on here? But you see those clouds come ahead as you see that anvil coming out, and then you see some of those old storms dissipating, and when they dissipate, the rain shafts kind of disappear, and all that's left is the anvil and the tops of the storm clouds. You don't see the base anymore because now it's back here where your main where that main inflow. You got your convergence. You may have winds coming from different directions. This when you get that mesoscale convective system, and you see those new towers develop. It's kind of a regenerative cycle here. This is just another angle, another look at how those MCS storm systems work. And here's a look at one on the radar. This is your mesoscale convective system. You see they kind of take on a quasi, kind of like an oval shape here, because what you're seeing here is the top. You're seeing those towers come all the way up, and it hits the stratosphere. It hit the tropopause, and it can't go really past that. Some of the tops might overshoot into the stratosphere a little bit, and you'll see it spread out. This is a lot like a hurricane look. You just don't see an eye here. You see the resemblance here between a hurricane, because you have, it kind of creates its own central area of low pressure, and it gives it that round shape here. This is a mesoscale convective system. And then here's what they look like. You know, this is what you'll see. This is what I was talking about here. You see this shelf cloud right here as that storm coming in, and you see that area of main heavy rainfall and that gust front. This is called a gust front. And you see that updraft here. This is the updraft of the air coming in. This is your inflow into the storm. This is your mid-level flow outward coming out of the storm, because some of that flow as it comes in gets diverted out because you have the upper level winds that's pushing the storm. So some of those winds get diverted out and head out that way toward the front of the storm. This is the anvil. You're looking at the anvil of your thunderstorm here. And that is a beautiful shot of a shelf cloud coming in from a mesoscale convective system. And here is a look at your mesoscale, your multi-cell thunderstorms. You see your older storm here that's in the mature stage, maybe starting to dissipate a little bit. You can kind of look at the clouds here. One way to tell if a storm is precipitating, look at the top of the clouds. If it looks kind of shaggy, looking kind of shredded a little bit, that's an indicator of that icing, and you can see that the icing is falling. But if it's still sharp, that cloud is still building. It's not precipitating. It's still rising. If the tops of the clouds look sharp and ragged and really defined, but if they look kind of shaggy a little bit, that's usually a storm that's in the mature stage or beginning to go into the dissipating stage. And this is what I'm talking about here. Now you see these guys here, these white pillowy clouds. That's a new cell developing out ahead of this guy, because creating that downdraft that's also causing that warm air out ahead of it to lift. So it's helping to generate new thunderstorms there. So that is a multi-cell thunderstorm. Here's another look at a multi-cell storm that you got 1, 2, 3, and 4 as you got multi-cells. Now you got your older storm here, another storm developing, another storm behind that one, and another storm behind that. And usually what you're seeing with this guy is that they're moving like this. In the parallel, they're running kind of horizontal here. They're not really moving forward. This is what you're seeing. So you'll see the front storm go through its life cycle, rain itself out. Then the next guy will take over, go through its life cycle, rain itself out. And then this one will come in. So you're just going to get repeated training of thunderstorms. It's like, man, they just keep coming. And you'll think it's the same storm, but you're really experiencing different thunderstorms at different stages of development. And here we are looking at another multi-cell cluster of storms. So we're seeing one developing here, one developing there. You see that multi-cells is a very active day wherever this is taken. And here you are, another cell over in that region. So now here is a mothership. This is a supercell thunderstorm. Now you see these guys, this is called a mesosphere. This is a meso-low. So this guy is rotating. You'll see this is your wall cloud here. You see some lightning there. Your tornado would appear somewhere in this region right here. It would probably be a rain-wrapped tornado with this storm system, but you do see that mesosphere and that rotating. A lot of times, supercell thunderstorms rotate. That's what allowed them to be long-lived thunderstorms, because they get so much energy going that they become area of low pressure all in themselves and start to rotate. And when you see that rotating column of air, then you're going to expect to see your tornado. These are also your storms that have those very violent updrafts. You'll see that large hail. This is probably what this is large hail falling from this storm. This storm, I think, produced a tornado. I believe this one was in North Dakota. I tell you what, you think Oklahoma and Texas produced beautiful tornadoes and storms. North Dakota, southern Canada, Alberta, the high plains into Colorado, Wyoming, eastern Montana, they're no slouch either when it comes to beautiful thunderstorms and scenic thunderstorms. They usually develop a lot of elevated storms. So it's pretty beautiful as well. Here's another look at a severe thunderstorm. This one actually has a shelf cloud attached to it too, ahead of it as it moves out. But this one also, you see that these lines here is because they rotate very fast. And these rotating thunderstorms, once again, we have a beautiful storm there. Now we're going to look at another look at a low precipitation supercell here. Another rotating superstorm. This storm actually, I think, produced 2 or 3 tornadoes here in Oklahoma, as we have this very powerful mesoscale low pressure center here in that rotating thunderstorm. They're really spooky and scary to look at. They're really awesome, but if you're not used to that, they can be quite frightening, and you're like, whoa, what's going on here, And here's different types of lightning. Here we're going to talk about lightning now. Lightning is really interesting because you don't necessarily have to be close to or under a storm to see lightning from a storm. I used to live in Florida and Arizona, and I can't tell you how many times I saw lightning shoot across the clear sky because the storm was like 5-6 miles away and cloud to air lightning. So we're gonna discuss the different types of lightning now. So we have your intra-cloud lightning, we have your anvil crawlers, anvil lightning, and then we cloud to ground, cloud to air. Also, there is going to be your bolt from the blue, which is interesting. That's very rare there. And we're going to have your ground to cloud and a spider lightning, as well as sprite. Now, we don't know a whole lot about these here. Sprites and jets are a whole different realm of science there. I'm not going to cover too much of that in this video because that's a lot more to explain, and I don't have all the facts when it comes to those guys there. I think there's some kind of exhaust from the cloud to ground lightning. I don't think all lightning produce sprites and jets, but I think what they are now, sprites are interactions with the Earth's magnetic field. So when you see sprites, it's because it's interacting with into the stratosphere. And when you have those thunderstorms with overshooting cloud tops that reach into the lower levels of the stratosphere, those storms are usually pretty tall and generate those sprites and jets and things like that, because that that energy is interacting with the Earth's magnetosphere. So here is a look at some spider lightning in the anvil. This is also called anvil lightning or anvil crawler, right? And then we have your cloud to ground lightning right here. Now this here, when you see the lightning and has a lot of arms and fingers like that, that is usually negatively charged lightning there. Now, if it's a single bolt and you don't see all these stragglers, that's positive lightning. All right. So I don't have a picture of the positive light. Maybe I do, but we're going to look at this negative charge here. Now we have cloud to ground, ground to cloud lightning. Now this is kind of rare, and you see this a lot in the Midwest and the Central Plains states a lot. And you'll see the charge here where you have the positive charge at the surface and the negative charge in the clouds. You'll often see this with the anvils of the clouds as well. You'll see that cloud to ground. This lightning is very vivid because it travels a great distance from the surface to reach the anvil of a thunderstorm, which could reside at about 20 to 30,000 feet. All right, so now we're going to look at your cloud to air lightning. So this is the lightning that I saw a lot in Florida and Arizona during the monsoon, which you can be clear where you are, but you'll see this bolt of lightning just shoot straight out. Some people call it dry lightning as well. Well, not dry lightning, but what do they call it? They call it heat lightning, yes. But there is no such thing as heat lightning. That is bogus. So when people say heat lightning, correct them. Tell them Dooley says there's no such thing as heat lightning, okay? But this is cloud to air lightning, because that negative charge can be in the atmosphere as well. So sometimes you'll see those bolts shoot out into the ether. All right, so here is another look at some anvil crawlers here. This is some of my favorite lightning. This is very vivid, and because of the high altitude that it occurs at, and you'll see this a lot when you have MCSs, so mesoscale convective systems. You'll see that a lot with those bigger thunderstorm complexes with large anvils. You'll see a lot of anvil crawlers there. So here is ball lightning. Now this is very rare, and believe it or not, I have seen one of these things before. I was at a buddy's house and we were standing out at his front porch, and we saw the lightning travel down the power line. It was in slow motion, just traveled down the power line from the power pole, and it exploded by his front door where the power line connected to the house, and it came down, said pow, a big old explosion. I actually saw ball lightning. Not much is known about, we're not sure what creates it, so it's one of those things I just wanted to show you just to let you know about it. But it's kind of rare to see, so not a lot of research has been able. Now they've been able to kind of sort of recreate the conditions in the laboratory setting, but we don't think, we think it's just a positive charge that kind of gets detached from a storm system and maybe travels through inanimate objects. Like you see this one on the railroad lines here, or power lines. It usually needs a conductor. They don't just appear in midair. They usually probably take a charge from another lightning strike that struck something, and that energy kind of condenses in that single area, and then that charge just travels down whatever the initial lightning bolt struck. That's how it's believed to occur, but no one knows for sure. It's kind of an area that's kind of, all right, okay, whatever. But it's rare. But if you ever see one, you are in a special place there because they are rare to occur. So here we are. We're looking at your tornadoes now. So what we're seeing here is, like I mentioned previously, when the tornadoes, you get what's called shear. We talk a lot about wind shear and how it leads to tornado development. And what wind shear is air turning with height as it moves. So you may have air coming from two different directions at the surface, but as you go higher in the atmosphere, that air pattern changes. That wind direction changes as you increase your altitude. And what happens is that once it meets a storm and you get the outflow and you have the inflow, and it creates a spinning column, a horizontal column, then that horizontal column gets lifted by the updraft. Now it's vertical. It becomes vertical, or maybe slightly vertical, maybe an incline there, and that determines what kind of tornado you're going to have. And then once that really fully connects and your tornado gets going, this is usually how it looks internally within the clouds. You see that spinning column that rises all the way up to the atmosphere from the surface, all the way through the cloud. This is your tornado right here once you get this process going. Now, that spinning column increases in speed because of the rotation of the cloud. So that tightens up as that rotation solidifies in that storm, and then you start to see that funnel cloud. And because it's area very low pressure, it's because that pressure is very low. But really, if you really dig down deep into a tornado, the pressure is inside of it's like a hurricane. It's actually quite high, so it makes that finger, that tornado, come down, because the very center of that tornado is high pressure, but it's very low pressure around the outside of the edges of the tornado as it spins. So it's like a hurricane. It's the strongest around the eye wall of a hurricane, but the center of a hurricane is clear, because your center of the hurricane is sinking air. That's why tornadoes drop down, because the very center of the tornado, even though can be a really small, tight rotating area, but it drops down. And that's why tornadoes drop down from the clouds, because the very center of the tornado is really high air pressure surrounded by equally low air pressure. So now, as we're looking, here's a better look of what that tornado looks like. You see here, let me stand over here. Now you see that inflow, how it's rotating. You see your rain and hail here. You have that rotating column, but it meets that updraft, which turns it upright. So the updraft makes it upright, right? And then you have your column. Now it creates that column. It kind of breaks off here. It breaks. You have that column. It goes up. That updraft goes up, creates your outflow in the top of the cloud. But now you have your lower half of your spinning column here. It breaks off about the mid levels of your storm here, and that inflow is constantly coming into your tornado here, so it's increasing that wind speed because of that inflow. So now you have your inflow. This is why you always see rain, hail, and tornadoes kind of go hand in hand, because the conditions that create the hail also lead to the creation of your tornadoes, because you need really strong updrafts. And we're going to talk about hail in just a few minutes here. So here's a look at some of the different types of tornadoes out there. This is what we call a wedge tornado. This is usually one of your most dangerous types of tornadoes, but your size of the tornado that you actually see doesn't always mean that it's the stronger tornado. So how wide a tornado is have very little impact on how strong the tornado is. Not all the time. And sometimes usually your wedge tornadoes tend to be stronger tornadoes. I'm going to stand here so you can kind of get a look at the size of this thing. This, I think, is a visual of the El Reno tornado in 2013 in May in Oklahoma that took the lives of several prominent storm chasers. So my condolences go out to the family of those storm chasers that lost their lives in the El Reno tornado. Now, the thing about the El Reno tornado was it's the widest tornado ever recorded. It hit a width of 2.6 miles, and a lot of people, and it had a very erratic movement as it kind of went from the south, went to the east, kind of wobbled to the southeast a little bit, and then turned to the northeast real quick. It kind of went like this, and tornado, it kind of wobbled. It had a very erratic path as it moved around, and some of the storm chasers got trapped because they didn't expect the storm to change direction the way it did. So condolences to those storm chasers out there. And here's what we call a rope tornado here. Now this is your rope tornado, and this is kind of one of the most common tornadoes you see. You really see this one a lot in the northern plains, and usually the storms that produce these tend to be elevated. Usually your wedge tornadoes are lower base tornadoes or thunderstorms, but when you get an elevated storm where the cloud bases are a little bit higher in the atmosphere, you tend to see these skinny tornadoes, these rope style tornadoes. Now, here is what we call a stovepipe. Okay, now, these guys are creepy. This is the creepiest tornado you will ever see because they move erratically. And remember how I was talking about that updraft that gets lifted up? Sometimes that updraft don't exactly go straight up and down. Sometimes it's at weird angles going in and out. But that updraft is kind of how the shape it takes. So you'll get these stovepipe tornadoes, and it's because they look like the pipe on the old old wood-burning stoves back in the day they used to have, in those weird pipes for the exhaust, so that you wouldn't die from carbon monoxide or smoke in the house. But that's why they call stovepipe, because they look like the old stovepipes from the stove back in the 1800s. So this is one of the creepier thunderstorms you see, and you often see this with low precipitation thunderstorms as well. This is a very common storm in the southern plains and the central and northern plains. You'll see this out in Nebraska and Kansas a lot, maybe Oklahoma. You'll see these crazy looking tornadoes. So now we're looking at a cone. This is a cone tornado. This is probably the most common type of tornado that we see out here. Now these can be very dangerous. Now these can often hit F4, F5. These kind of tornadoes do a lot of damage as well. These have taken a lot of lives, as well as wedge tornadoes. Wedge and cone tornadoes, I think, have been the most dangerous tornadoes that we have in existence. And now we're going to take a look at gustnados. Now, gustnados aren't really tornadoes, but they're kind of like dust devils in a way. But they are basically tornadoes, kind of, sort of, that take place at the surface. They're not connected with the thunderstorm itself, but because you have little eddies on the surface by the inbound and outflow of the storm. You got the inflow, you got your rear flank downdraft. This usually occurs in your rear flank downdraft, and this is kind of like your mid-flow of the storm. That there's a mid-level flow of the thunderstorm that the air comes in, and you have a backdoor inflow into the storm, and it usually creates these little eddies on the surface. They're often very weak, don't cause a lot of damage, kick up a lot of dust maybe and stuff like that, but they're about maybe 40, 50 miles per hour winds. They're not very dangerous, but they are kind of interesting to look at, and can, you know, make you think that, okay, they often mistake these for tornadoes, but they're not actually tornadoes. So now we are looking at a hail producing. Now here's how hail forms. Now, when you have hail and you have your warm draft, your updraft, now the updraft picks up rainfall. So when you have really strong updrafts in your supercell thunderstorms, where the updraft overpowers the downdraft, so what happens is that you will see that inflow and the rainfall gets picked up by the updraft and then taken back for a ride through the layers of the cloud again, and it freezes. So it forms little ice balls. So every rotation, every cycle that hailstone takes through that cloud, because of those really strong updrafts, it grows. It gets bigger and bigger and bigger. The stronger the updraft, the bigger the hailstone is going to get, because as they travel through the clouds, they collect other water droplets within the cloud. They coalesce together, a lot like planets do in the formation of the solar system, of solar systems. The planets accrete together with other dust particles around them, and they pack together and form planets. Hailstorms kind of form the same way within a thunderstorm. So your thunderstorm is your accretion disk, so to speak, in astronomical terms, and it picks up the hail and it takes it for a magic carpet ride back and forth through the storm until it just becomes too heavy and the storm can't hold on to it. Then it falls back to earth as hail. Usually you see this in situations where you get tornadoes, because the same function that's lifting the hailstones up is also lifting that column of rotating air upright for the spinning of a tornado. So hailstorms kind of form that way. That's how hail is created. Now, here's an example of some of those hailstones. I expect to see hailstones like this weekend, with this weekend's severe weather threat coming up for your Friday and Saturday. And here's a smaller hailstones that you'll see as well. So there's some more hail, and we have another look. Here's another thing with severe weather that you have to watch out for. This is usually an issue for people flying. So if you're flying in an aircraft and you're coming in to an airport. I remember some years ago, back in the 90s, I think, a plane crashed in Dallas because they were coming in for a landing and they got hit by a microburst from a thunderstorm, and the microburst slammed the plane into the ground out of the air, snatched the plane out of the air as they were flying in, and they hit that microburst and bam, that plane just slammed into the ground. I think there was like 100 people on board and everybody perished on that flight. So these downbursts and microbursts occur when thunderstorms have that heavy rainfall, and sometimes that cold air starts rotating in the upper levels of the clouds. As you see, it comes into the inflow of the cloud, but it kind of gets squeezed together. And as it gets squeezed together by all the inflow, you get the downflow and you got the inflow. It's all kind of compression, and then it comes down with a great amount of force as it gets dumped out of the cloud by that heavy rainfall. Usually these storms have a lot of heavy precipitation, but this is not falling with the precipitation. It's kind of out ahead of the precipitation. It's a little bit different than downdrafts, because downdrafts can cover a wide area. The width wide can be wide, but microbursts can be small. That's why they're called a microburst, because it's a small area, but it's winds that can kind of rival some tornadoes, and it can pack winds 100 miles per hour plus, coming straight down out of the base of a cloud. So this was an airliner that got hit, but small planes are no match for some of these microbursts and downdrafts like that. And when these microbursts hit the ground, what happens is they create this vortex ring, because that air hits so hard that it kind of reverberates back up again, because it's kind of like when a meteor hits the earth and it makes that dust, that pulverizing poof pop up when meteorites collide with the earth. Kind of same thing happens with this. It kind of creates kind of the same ring in the air that meteorites do when meteors hit the Earth's surface, what meteors do to the ground, and it creates that ring, and you see that little cone in the center. This kind of does the same thing with that air, because it hits, boom, with such a heavy force. So here is an example of some of the effects of these microbursts, downdrafts, damaging winds with some of these severe thunderstorms. You see that, and the trees kind of all lean in the same direction because the wind is blowing in the same direction, kind of sweeping across the landscape. Here's another example of, you see all these flattened trees. This is from a microburst or straight line winds out of a thunderstorm. And that was a look at some of different modes of severe weather that we have out there, and how some of those storms develop, and just a detailed look at the different types of severe weather that we deal with out there from day to day, especially through the spring and summer months. But severe weather can occur year round here in the United States. My name is Dooley Godot. I hope you enjoyed this video as much as I enjoyed making it, because this is my area of expertise. So thanks for watching. Please leave your comments and your likes there. It would be appreciated. And subscribe to the channel. And I'll be back in the next video. Have a great day. And remember, be safe out there, as we do have a lot of severe weather in the forecast as usual.